Let's move to lecture 3, diffusion equation and its corresponding solutions. So, give you a quick review. Don't forget the way we are interested in how to quantitatively analyze the kinetics process, especially in atomic transport. So in lecture 1 and 2, we put more efforts on introduce you that we use a sigma dot, which is entropy production per volume to describe this, quantitatively describe this kinetics or atomic flux, atomic transport process, kinetics process. So if you use that idea here, you probably will write it down. Absolute temperature times the sigma dot equals to atomic flux times its driving force, which is a negative chemical potential gradient. And if there's no other driving force here, the atomic flux here probably can be written as negative mobility concentration and the chemical potential gradient. So you simply turn them together, so you will get this results: mobility concentration and chemical potential gradient. And you have a square here. So it turns out that you have one difficulty to answer: what's a sigma dot? Because as a scientist, it's quite difficult to measure the chemical potential gradient, right? Usually we measure the concentration gradient instead of the chemical potential gradient. So Einstein relationship also tell you that the chemical potential gradient is a function of concentration gradient. So you can substitute chemical potential gradient in terms of concentration gradient here. So then we can rewrite these equations. So we got the sigma dot, which is the entropy production rate per volume, equals to K KD divided by C and concentration gradient or concentration gradient square. So now it's much easier to calculate or estimate sigma dot. Why? Because as long as you know the concentration gradient, you substitute here, you know the diffusivity, you know concentration, and this is a Boltzmann constant, then you know the sigma dot. So let's results interpret why we need to uh, learn this lecture. Because how to get the concentration gradient will depending on diffusion equation and its corresponding solutions. So as long as we know we can get the diffusion equation and get its corresponding solution to know how the concentration of diffusing atoms change with location and time and substitute here, then you will have chance to know the sigma dot. So this is the whole story to you to interpret why we need to learn the diffusion equation and its solution. The answer is we want to know how the concentration of diffusing atoms changes with location and time. This will help us to substitute this term and get a sigma dot. Okay, so in this lecture 3, we will we will simply separate into 4 sections. The first one is the diffusion equations to help us know how the concentration of diffusing atoms or your interesting atoms change with location and time. Then in the second sections, we are talking about 2 conditions. The first one is the steady state. The steady state means the concentration does not change. The concentration of your interesting atoms does not change with time, but we do have a concentration gradient on our materials, but the concentration distribution does not change with time. But what is the non-steady state solution, which means that we also have the concentration gradient, but the concentration profile does change with time. We call it as a non-steady solutions. So in this case, you need to know how this concentration profile changes with time because it does change. But so you need to know how the concentration changes with time. And the third part will be talking about in prior studies, in order to simplify all questions or all conditions, we assume the differentiability equals to constant. So that can help you to simplify the differential equations, right? But in some case or in real case, the concentration usually sometimes will change. The differentiability sometimes will change with concentration. We call it concentration dependent differentiability. So under these conditions, we have a differentiability dependent, concentration dependent differentiability. How to get how the differentiability change with concentration? We will introduce you one method or one analyze method. We call it Boltzmann-Montano analyze. And before we end this lecture, we will talk more about we have in the case we always deal with is we assume the system is isotropic differentiability, right? But however, if your crystal is not isotropic crystal, for example, like a tetragonal, a monoclinic or triclinic, or hexagonal, this crystal with different variation, different degrees of anisotropic. Some crystal, you have anisotropic crystal structures. So how we modify the differentiability, how to deal with their differentiability. So we will talk about this in the last sections. So let's move to the first one, diffusion equation. The most you familiar diffusion equation only limited in diffusion equations in solid materials. But actually, the same idea can be can help you to know the temperature and also the electrical potential distributions, which means that we can use the same idea and to get the temperature distribution, how the temperature change with location and time, and also same does the electrical potential. So that's starting from how we get the diffusion equation. So we're starting from the continuity equation for mass transport, right? So also, if you want to know about the temperature and the electrical potential part, then you also can use the continuity equation for heat transport and also the charge transport. But we're starting from the one you're familiar with is mass transport. So as we have shown you before, continuity equation for mass transport, Ji, can be written as a concentration, how the concentration change with time equals to the source or sink, the rate of generation or depletion of mass per unit volume, which means that this box, your interest box can, if it can generate or deplete some atoms, plus the flux surrounding given to you. So this is we call a continuity equation for mass transport. But here, usually we always assume there's no source and sinks operated. So this equals to 0. So the concentration change rate only happens on the interaction between the surroundings. So we can write down this general form can be concentration change rate equals to negative flux gradient. And also the flux here obey fixed first law, so you can write down equals to negative differentiability concentration gradient. Negative, negative, so you got the differentiability concentration gradient. So this is the general form we call a fixed first second law. And further, if we assume D differentiability is constant, then you take the D outside this gradient operator. So you got this diffusion equation. And this is what we call a Laplacian operator. Okay. So this is a typical diffusion equation you learned before. But the same continuity equation can also be applied for heat transport and charge transport. So this is what we have derived here, right? So I want to show you how to use the diffusion equation or continuity equation for heat transport. So the heat change rate, it can be rewritten as negative the gradient of flux. So you can compare here, you just substitute the concentration as heat, the atomic flux as heat flux. Then, and the same idea for charge, right? Concentration, you can substitute as the charge. And here you can substitute as current density. So next, I'm going to show you how to derive the diffusion equation for heat transport and also electrical transport. So the total heat will be equals to Cp dt, right? But because the final unit will be per volume, so I times the density here. Then the heat flux obeys Fourier's law, should be negative thermal conductivity times temperature gradient. So don't forget this times the density is due to we use the per volume for everything. Okay, so next we just move the density and heat capacity move to right-handed side and arrange it. Then you can see that we got the temperature change rate, and you gather this temperature gradient times this kappa divided by density and heat capacity, and you take the second gradient on this term. So this is, some people call it as a thermal diffusivity, similar with diffusivity, atomic diffusivity for mass transport. Similar, right? So this is, some people call it as a thermal diffusivity. So in order, as long as you solve this diffusion equations, for heat transport, you can get how the temperature change with location and time. So the same idea for electrical charge. The charge here, you can use the CQ d phi. CQ is a capacitance. You times the d phi, so you got the charge, right? Sometimes if it's hard to remember, you can check the unit here. And the current density obeys Ohm's law, so negative electrical conductivity times the electrical potential gradient. So the same idea, I just move this to the right-handed side and to become here. So this is the electrical potential change with time. Then you got the gradient term is the electrical potential gradient times the conductivity divided by capacitance, and take the second gradient on it. So the same idea, similar, right? So as long as you solve this diffusion equation for electrical transport, then you can get how the electrical potential change with location and time. So this is for your reference. So I just hope this slide can help you to know that diffusion equation not limited in mass transport. You also can use to help you to know the temperature distribution and also the electrical potential distribution within your interesting subject or research. And one more, I want to remind you that for electrical part, there's a very famous equation we call the Laplace equation, which is we take the Laplace equation is we take the second gradient for the electrical potential equals to 0. This is we call the Laplace equation. So actually, this have some physical meanings for Laplace equation. Is that the similar with this one? Actually, is there's no your interesting cubic or your interesting system. There's no how many charges move inside equals to how much charges moved outside. So there's no charge accumulation inside this your interesting box. We call this is a Laplace equation. If there's some charge accumulations, then the equation we will call you that equals to 0. We call a Poisson equation. Okay. And the other question, probably some people will put more emphasis on Laplace equation. Does the electrical potential need to equals to zero under Laplace equation conditions? Not necessary, right? Because you take the second gradient equals to zero, only tell you the gradient, what? Gradient equals to constant. So that will lead the second gradient equals to zero. The gradient equals to constant just tell you the electrical potential don't have any local maxima or local minima. Okay, so not necessary to be zero. Okay. Okay. Then this is just for your reference, just for reference. And now we move to second section. We were going to introduce the steady and non-steady solutions. The boundary conditions are different, and they also have different solutions. For steady state, which means that we do provide a concentration gradient on our systems, but the concentration profile does not change with time, which means that concentration profile always keeps the same. This is what we call a steady state. But as we mentioned, if the concentration profile does change with time, is the case we call a non-steady state. But both cases they do exist the concentration gradient acting on these materials. So starting from the simplest one, which is the steady state solution or steady state conditions. What we have here is we have chemical solutions within this you can consider as a dialysis tube. And at two ends of the two sides of the dialysis tube, we allow the concentration C0 and CL remain constant. So we do have constant boundary conditions. And the dialysis tube, the length for this dialysis tube is L. And we try to measure the concentration profile within this dialysis. And we find this profile, this slope. And after different time point, we measure the concentration profile again. Then we find this concentration profile does not change with time, always looks like this. So what the question will be, what is the flux? And can you prove that these conditions are steady state? So in order to know that, we can make sure that this concentration profile does not change with time. So partial with t equals to zero. So based on the diffusion equation, this equals to zero. We assume that the Laplacian of concentration equals to zero. So based on these ideas, we also need to, because you need to make sure D is constant, then you can make these conclusions. Okay, then what's a flux? Flux equals to negative diffusivity concentration gradient. So I need to write down how the concentration change with location. So based on these results, Y is C equals to AX plus B. X is a location, slope. So I got the slope is CL minus C0 divided by XL, X plus C0, because this is 0. So this is C of X, how the concentration change with location. If you don't believe that, you can double check. I put the C0 here, X equals to 0. So I got C equals to C0. And if I put the L here, I also got the C equals to CL. So this equation works. So I just put here, I don't need to know the flux. I just gradient with X. So this term, diffusivity times this term. So I got the flux. Flux is a constant flux. Why? Because D is constant, L is constant. L, C0 and CL are constant as well. So we got a constant flux. Constant flux means a steady state, right? So the characteristic for steady state is constant flux. How much atoms moves inside your target? How much atoms moves outside? So there's no accumulations of atoms into your interesting box. So this is constant flux. Okay. So for non-steady state, it's more complicated because it turns out we do have a concentration gradient, but the concentration profile does change with time. So you need to have extra time. So the concentration partial C partial T not equals to 0. So things complicated. So now you know the concentration does change with time, not only change with location. So in this type of systems, you need to find out what's the material system and pick up and find out how many driving force to drive this mass transport. Then that will help you to formulate the diffusion equation, and with its initial boundary conditions, I hope you can guess how the concentration change with location and time. So chapter 3 will focus on with the boundary, initial and boundary conditions will help you to get the corresponding solutions for this diffusion equation. So we will show you step by step. But based on this idea, you know that you need to figure out what's the initial and boundary condition. That will help you to get the corresponding solutions for your interesting systems. So there are three typical diffusion, case we are going to introduce to you in this non-steady state conditions. The first one is we call a diffusion couple, which means that you have A materials bind with B materials. So we call a diffusion couple. Couple means the two bind together. Diffusion couple. So when you try to plot if you are try to plot the A, if I use A, concentration for A atom, you will get here concentration. So in B material, we don't have A, right? But if you try to plot, B, if I use this to represent concentration for B, then we don't have A, or we don't have B in A materials. So in the beginning, like this. So this pictures actually is drawn by A. So it was in the beginning it was go like this. Then okay, the concentration will decrease. If you take a look on this specific location, the concentration decrease over time. And here the concentration increase over time. So this is for material A. Okay. So this is what we call a diffusion couple. And next would be the surface constant. So the case 2 actually, you can draw them. Case 2 is here. You have the substrate, but I called it a thin layer of targeting diffusing atoms on the top of your substrate. But this is a thin layer, 有限的很薄的。So in the beginning, the concentration is quite high, but as time increase, the concentration profile decrease. So this spread more deeper. So this is we call a surface concentration decrease case. This is limited source. So I as I mentioned, I emphasize this thing is a thin layer diffusion source. And the third one, actually, we call a concentration. It's similar with this one, but only also substrate. But I give it a unlimited source. Unlimited source. unlimited source, and the concentration always fixed at SC, and is unlimited source. So as time increase, diffusion, as time increase, you can check like at specific time point or locations. It was here, but with time increase, the 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 concentration of diffusing agent increase as well. But no matter is time T1 or T2, the surface concentration always fixed at C0, Cs. Because we provide the unlimited diffusion source on the top of it. So probably can be I get a very thick layers deposit, or I flow to provide a flow the diffusing atoms. OK，它可以是你镀一层很厚的在上面扩散原子，或者是你用气体的方式通足够量的固定浓度的 diffusing atom 都是可以的。OK， so let's move to the first one, diffusion couple. So the first one, so next following slide, I just want to show you how to solve this diffusion equations. So that will involve some a little bit complex mathematical tricks in the following slides. So I hope you can follow me step by step. So this is the diffusion equation. Then we need to show you how to scaling of diffusion equation. So this is diffusion equation. We have assumed that D equals to constant. So you will get this diffusion equation. Concentration change rate equals to diffusivity. Then we take the second gradient or second partial with the x. So this you can see two variable x and t. Okay. Then how to get this partial differential equation with two variable x and t? We need to introduce a dimensionless variable iota. This iota with the x and t. Then the purpose here is we want to convert this partial differentiation equation with two variable to one variable iota. So this is we allow or introduce this iota equals to x divided by square root of 40t. And we need to use the chain rule first. The chain rule tell you that partial c partial t equals to partial iota partial t partial c partial iota. What this means? Chain rule actually is partial c partial t partial t partial iota and partial iota and partial c equals to 1. You got this, so equals to 1. So I just convert this one to right-handed side. So you got a iota t converted inverse, right? Partial c, partial iota. Okay. Then partial iota. So the final goal is I want to get the partial c, partial iota. So here I got a partial c, partial iota. So partial iota, partial t. So you use this partial with t. So you got a negative iota divided by 2t. Okay. And right-handed side, because you have d and this, you have a second, you have a concentration, a gradient with x. Okay. So this is quite easy because for this, usually I will do one way because x equals to square root of 40t iota. So I just put here square root of 40t iota here. So 40t square root square. So you got a 40T outside and iota inside. So you got successful to get this one. So left-handed side, I converted here, and D, and this I converted to concentration, take the gradient, secondary gradient with iota. Okay, so I can put here. So I got the ordinary, I successfully to get the ordinary differentiation equation with one variable iota. So afterward, I just solve this results. I will know how the C change with iota. So we are close to the answers. Okay, so single variable. Okay, so now I just copy this result here because this is what we need to solve, right? So back here, this actually, you can consider this is uh, you have a concentration change with iota. So this is a step function, one dimension step function, 一维的 step function. And it was beginning because diffusion couple in beginning, it's like t equals to 0 is like the step function, right? As time increase, then the atoms will move to left-handed side. So it was CR at right-handed side, CL at left-handed side, right? So how to get this one? So in order to, this is mathematic trick. So I allow DC over the iota equals to Q. So I can rewrite this equation, negative 2 iota and Q. This is Q. Sorry. So I will use Q. This is Q, and this just dq over the iota because this is take the secondary gradient with respect to iota. So here, so that's help to, so this equation let us solve the Q. Here is A1 exponential negative iota square. So this is a typical solution for this type of differentiation equation. You can, if you don't know how to do that, you can move this d iota to right-handed side, Q to right-handed side, then you take um, the integral for both sides, then you can get these results. So finally, I need to solve this equation. So this is also easy. You just need to move the iota to left-handed side, take the gradient integral on both sides. So this is how we deal with. So if you do that, then the C, you take the gradient, and the button, you need to have a button. So a button limit, so it's from negative infinity to iota. So take the negative infinity to iota. So you got this. So negative infinity to iota, and the dc, if you take the integral on this one, the button is negative integral and iota. So you got the c of iota, negative c of negative infinity. So this is the result you will have. So if you take a look on here, this term is quite familiar with what you learned in arrow function. It's quite familiar with, right? And just a quick review for arrow function. Arrow function is an odd function, so arrow function 0 equals to 0. Arrow function infinity equals to 1. And it's odd function, so arrow function negative z equals to negative arrow function z. So this is some property for arrow function. 0, 0, infinity, 1. Okay, so based on here, I just want to, in order to answer this, I separate into two terms. Negative infinity, I separate to negative 0 plus 0 to iota. The reason is I want to make this term more similar with, to allow me to substitute with arrow function. So I separate them into two terms. And this is negative infinity to 0. So, and this is 0 to infinity, okay? So, and here to here is I just keep here to move right-handed side. C at negative infinity, the concentration is Cl. So negative Cl, move to right-handed side Cl. Okay, And here to here, actually, I play a trick here because negative to 0, negative infinity to 0 is like this term, right? Because I want to use the arrow function. So you can this one is similar with this one, right? So I use the 2 divided by pi, square root of pi, and negative infinity to 0. This is identical is an arrow function, but I times the a2. A2 is pi, square root of pi divided by 2. A1. So I just if you put the list to here, I just want to make an inside term as an arrow function. So I just do some parameters exchange. So this is the same idea, right? So I times the 2 divided by pi, then I divide it by this term. So that will make them together. And take a look on this term. This one actually is arrow function 1 because negative infinity to 0. So if I switch the upper limit, lower and upper limit, I will get a negative 1, right? So it will be 0, negative infinity. Negative infinity, I can take the negative outside, negative 1, negative 1, I got a positive 1. So this is 1. And this is arrow function, typical, identical with arrow function. So so at this moment, I need to uh, boundary condition to help me. So when the infinity approach to the iota approach to infinity, the C will be equals to CR. So at this moment, I got A equals to this. So A2 equals to this. So I substitute back here. Then I got this results. So you need the help from the boundary condition. The one actually you haven't used. Actually, beginning you have used a CL, right? But you haven't, CL is here, but you haven't used a CR. So use a boundary condition, then you know the A2. Since you take the substitute A2 back, then you will return the C will be equals to here. So this results is quite easy to remember because you just average of your average of the sum of right-handed concentration plus the left-handed concentration, and also the average of their difference, CR minus CL. Take the average on it and arrow function iota. So this is results, but just remind you, there's some location that the concentration does not change with time at 0. This point, actually the concentration always maintain here, the average of CR plus CL, and also at right infinity, the concentration should be maintained at CR, and at your left infinity, the concentration should remain CL. Under these situations, you can use these solutions. OK，所以在这里的话，这一题的话，它基本上是个数学问题。然后大家要记得的是，我们从这里到这里的话，基本上它是先令，因为这看起来就是二次微分，所以比较复杂，所以它先令它为 Q，所以你就会解这个。这里到这里是个正常解。那如果不太会解的话，就可以左边一项，右边一项，走两边做积分，就可以得到这个值。然后接着你再把它还原回来之后，就解这个。那解这个一样是抵 iota 到这里，然后两边做积分。然后积分的话，下限是负的 infinity，然后上限的话是 iota，所以这边就展开。然后这边sorry，这边唯一有 trick 是因为我们看它跟 arrow function 很像，所以就把它拆成 arrow function 的，因为 arrow function 都是用0作为分界。所以就拆成两项，然后接着，因为它跟 arrow function 的差别在于这边有一个常数，那我还是想把它换成 arrow function，所以我就先把常数放进来，你乘进来之后，你要再把它除回去，所以 A2 这里要除回去，所以你把这个 A2 这个放进来，你就发觉它们两个相除，就回到原来这个项，然后接着就是后面就没有，然后最重要是 boundary condition 要，因为这边这个 boundary condition 还没用到，在无限大的地方会是 CR。 然后这个的话，这个解蛮容易解，两边和的平均，然后加上两边差的平均，然后 error function iota，这个蛮容易记的。然后注意的话，你要用这个解的话，要符合这三个点。那最重要是边界条件，因为你用 error function，所以在 CR 的地方浓度在无限远这个边界的，它永远都要是 CR，然后 CL 要永远都要 CL。所以这个 diffusion couple 过往题目最常出现的问题是，就或你们过去在扩散学的是，它有让你估算说这个长度，就是它的这个 diffusion couple 的厚度要够，不然的话，这 CR 的浓度就这个 CR 就不会维持 CR，CL 就不会维持 CL。这种情况之下，你就不能用 arrow function，所以你不能用这个解，你当然这个解最后的解就会是不对的。但在彩洞里面不会要你算说它要多厚，但你就要记得 CR 跟 CL 它需要不随时间而改变，它永远都要是 CR 跟 CL，所以这 interdiffusion 的距离需要在中间，不能影响到两个边界条件的浓度。然后还有另外一个是中间这个浓度，它也是一个很有趣的点，它不会随着时间而改变。嗯，Okay, so usually I will provide you the error function and the table for error function